Linear algebra is the branch of mathematics that is concerned with matrices and vectors, their linear combinations, and operations acting upon them. Linear algebra has a long history in pure mathematics, in part because it provides a compact notation that is powerful and general enough to be used in geometry, calculus, differential equations, and many other areas of mathematics, not to mention other branches of science, including physics, engineering, and biology. So linear algebra is really all about vectors and matrices and how to use them. A vector is a list of numbers. It could look like this, or this, or this. So vectors can also be a list of functions. And a matrix is like a spreadsheet of numbers. In pure mathematics, you can have infinitely long vectors, and you can have matrices with an infinite number of rows and columns. But nowadays, most people are learning linear algebra because they need it for computer science or programming or data science or modeling in physics or biology. Vectors and matrices have a geometric interpretation that provides a lot of insights. And I'll talk more about this in a minute. One of the great things about linear algebra is that it provides a really compact form for expressing ideas in large data sets. That's why linear algebra is so important for big data. For example, imagine that you have a data set that contains time series data from 100 different sensors and millions of time points. You can refer to this very large data set using the capital letter X, so this is data stored in matrix X, and you can describe all of the linear relationships across all possible pairs of 100 sensors using this very simple, compact expression. And if you want to determine whether this really large data set can be characterized by a small number of important features, you can use eigendecomposition on this so-called covariance matrix, which is expressed using this compact and key formula. This equation is also called principal components analysis, and it's one of the most important formulas in dimensionality reduction and multivariate statistics. Another important aspect of linear algebra is combining vectors in different ways to achieve some computational goal. For example, you can use vectors to define axes in a high-dimensional space, and then use a transformation matrix to warp data sets or objects or other mathematical structures into and out of those spaces. This is really useful because some kinds of data analyses are better done in certain types of spaces. Furthermore, sometimes there is structure embedded in a high-dimensional data set like this that you don't necessarily see in the original data space, but that can be easily seen and easily quantified using a different kind of space after applying an appropriate transformation matrix. Here you see an example of this. This is a data set that lives in 3 dimensions corresponding to 3 channels. It just looks like a big unstructured cloud of dots, but that's just when looking at it in this space. I can warp it into another space, and then you can see there are interesting and meaningful features in this data set that are present in a lower dimensional subspace of this higher dimensional space. Now, in this particular example, I can solve the problem to a reasonable degree of accuracy just by looking at the data, because this is in 3 dimensions. But what do you do if you have 500 dimensional data? You can't just look at a 5-dimensional hypercube, and yet the linear algebra operations are identical for 3 dimensions and 500 dimensions. The ease and the power of transformation matrices is also why linear algebra is important for computer graphics, graphical programming, and geometry. Matrices can be used to encode translations, rotations, and stretching or compressing factors. So it's really easy to take an image and compress it or expand it along some axis. So here you see an example. This is a picture of an X-ray of a spine, and here I rotated the image. And the way that this rotation is implemented is by transforming all the coordinates in this picture to a new set of coordinates. And those new coordinates are defined by multiplication by this matrix. This is a transformation matrix. Now in this case, I rotated the picture by an angle of pi over 9, which corresponds to roughly 20 degrees. There is also a direct link between matrices linear algebra concepts, and geometry. And in fact, matrices can be interpreted as descriptions of geometric objects like cones or surfaces. Here you see an example of a surface that represents a matrix. This function that defines this surface is called the quadratic form of a matrix, and the quadratic form of a matrix is used to extract key features of that matrix. It's used all the time in statistics and in data compression, for example. So a little bit about terminology. Sometimes you hear the terms linear algebra or matrix analysis. Those terms are somewhat interchangeable with each other. The main difference is more about what these terms connote. So usually when people use the term linear algebra, they are referring to a somewhat more abstract linear algebra with abstract vector spaces, a bit more focus on theory, more focus on proofs. And in contrast, when people say matrix algebra or matrix analysis, they're typically referring to practical applications of linear algebra for real matrices that contain actual numbers as opposed to more abstract or continuous functions. Now, in this course, I'm going to cover both theoretical concepts and their implementations in computers for matrix analysis. So I suppose I could have called this course Linear Algebra and Matrix Analysis, but eventually it starts to become a mouthful, so most people just say linear algebra. I hope I've given you a bit of a sense of what linear algebra is and why it's important. In the next video, I will provide some concrete examples of how linear algebra is used in modern applications in physics, computer science, statistics, and data analysis.